So in this video, I'm just going to go through elastic potential energy. But before we do so, I think it's important to start with Hooke's law. And Hooke's law said that force is directly proportional to extension. So in other words, apply a force to a spring or a piece of metal and it will get longer, it will extend. And then he came up with an equation, and that equals F equals KE, where F is the force measured in newtons, K is called the spring constant, and that's all to do with stiffness. So the bigger the value, the stiffer the spring. And that's then multiplied by the extension, measured in metres. Just as a word of warning, quite often extension might be measured in centimetres, and then the unit will be newtons per centimetre. So there's a very simple practical for Hooke's law. You apply some mass on a spring, and of course, it will move down. And then from there, you can plot a graph. However, first thing to point out, mass is not a force. To find a force, we need to do weight equals mass times gravitational field strength. So in other words, any mass that you have, you need to multiply by G, which is 9.8 newtons per kilogram, or sometimes rounded to 10. First thing to do is think about maths. And in maths, when you draw a straight line, you will see y equals mx plus c. Well, if it's going to go through the origin, just here, then we know there's no plus c. So I'm just going to get rid of the plus c. So on the y-axis, if we put them equal to each other, we can put force. Plotted on the x-axis, we can plot extension. And then as we add our mass or add our force, the spring gets longer and our results look something like a straight line. Now again, if we compare our two equations, y equals mx with F equals ke, if we've got force on the y-axis, if we've got extension on the x-axis, and they're equal to each other, then it also follows that these two values must be equal as well. So in other words, m in maths you'll see it as the gradient, but in physics the gradient also has another meaning. It tells us the value of k, the spring constant. In physics we also have another equation, work done, or you can think of it as energy, equals force times distance. Now if you cast your mind back to a second ago, what we've got is a force acting down, the weight, and it's moving the spring a distance. So actually we are doing work. If you're pushing something, you're applying a force and it's going to move a distance. And the sort of graph that you'd get for that, a force distance graph, well, if you're applying a continual force, F, and that doesn't change, then of course the distance will get larger. The amount of work done, we said, was force times distance. You've seen that equation before. Now if we put some numbers on the force, well, let's say this is 10 newtons and it's moved 5 metres, we can see that that's done 50 joules of work. On the graph, if this is also 10 newtons and it's moved 5 metres, another way of showing this is by looking at the area underneath the graph, or by turning this into a rectangle where we have 10 newtons at one side and it's 5 across. So 10 times 5 equals our 50 joules. But with a spring, the shape of the graph isn't a horizontal one. The shape of the graph, as we can see, is a straight line, but at an angle. So if I remove this just here, now let's imagine we've kept adding a mass, or we've kept increasing the force. So let's put some numbers. And as we've added a mass, well, of course, it's got longer. So along here, we can add some numbers as well. So we've got a corresponding force of 4, and it's moved 6 centimetres or 6 metres. Well, if we want to work out the work done, from before, we said work done equals force times distance. But let's reword that. Work done is energy, so let's call it elastic potential energy instead. Energy stored in a spring. We've applied a force, measured in newtons, so that's the same as that one. But the distance, we don't call it distance when we use a spring, we call it extension. But both are measured in metres or centimetres. So what we can see here is elastic potential energy is force times extension. Apart from, that was for when the graph had a horizontal line. This graph actually makes out not a rectangle, but a triangle. And the area of a triangle is half base times height. Or a half, or the base along here, is the extension. And the height is the force. So really, elastic potential energy is a half times force times extension. And that gives us the area underneath the graph, like we did with our work done example. Let's just remind ourselves of Hooke's law, F equals KE. So now that we've got our elastic potential energy, and that half reminder because it's a triangle shape rather than a rectangle shape, Hooke's law, F equals KE, well, what we can do is rather than writing F, because F equals KE, we can put that together. So elastic potential energy equals a half KE times E from there, where that is KE. Two E's make a squared. So EPE equals a half KE squared. And that's our equation for elastic potential energy. That's the first one, and this is the second one. You get given this equation in the exam, so there's no need to remember it. However, you will need to rearrange it for the different things. So EPE, elastic potential energy measured in joules. K is our spring constant, same as in Hooke's law. And E is our extension. As a reminder, the squared just means that you square the value of E and not the whole thing, so you just square E. It looks very similar to the kinetic energy equation, and again you'll need to be able to rearrange that too, but you will need to memorise that one. But they look very similar, so that's a hint in the exam. You're given this, so remember it looks a little bit like that.